In this lecture, I shall be discussing the Dirac Delta function. Dirac, a famous man of physics, an English theoretical physicist, a Nobel laureate of 1933, was the first to introduce the symbol of delta of x, representing what is called the Dirac Delta function. Before going to discuss the Dirac Delta function, let me have a quick recapitulation of another type of delta function that is called the Kronecker delta function. Kronecker delta function is defined for discrete, that is discontinuous variable, and it is also denoted by the symbol delta. Here, the variables are alpha and beta, and they occur in the suffix of the delta called Kronecker delta. And if they are not equal, that is if alpha is not equal to beta, then Kronecker delta is 0. It vanishes, while if they are equal, then Kronecker delta is equal to unity. In contrast, Dirac delta is defined for continuous variable, and in the left slide, the x you see takes on continuous values and not values in steps like that assumed by alpha and beta. So, in Dirac delta case, the variable is not choosy but assumes all the x values. And another point is to be noted that x is written within a bracket sitting on the right of Dirac delta symbol, unlike that of Kronecker delta, which allows alpha and beta only to fall at its feet, as subscript or suffix. This is how we represent the delta functions in physics. Let us discuss now the Dirac delta function. First, let me specify why the Dirac delta function was defined. What makes it necessary to study the Dirac delta function, that is delta of x? Obviously, for discrete variable, we have Kronecker delta, and for continuous variable case, we need to have some quantity, and the continuous analog of Kronecker delta is the Dirac delta function. That is one point. Another point is that Dirac delta function has so many applications in various fields, and it has established itself as an indispensable quantity or tool in the study of science. Let us focus attention to the right slide. Dirac delta function that we will be defining soon has many applications in various branches or disciplines. In other words, Dirac delta function is a widely used quantity, that is, it is very popular. You can find Dirac delta function widely used in physics. It is used in statistics as well as in mathematics. Let me mention specific instances or a few places where Dirac delta function is employed in physics. With the help of Dirac delta function, some normalization problems in quantum mechanics are encountered or solved. These are well known as the Dirac delta normalization. Dirac delta function is also used in the theory of probability. To discuss signal processing, we require Dirac delta function. If we have a point charge, how can we describe or define the charge density? This can be done by using the Dirac delta function. If we have a point mass, how can we define or describe mass density? We can do it very easily and elegantly with the help of Dirac delta function. Also, Dirac delta function helps us in analyzing the effects of impulsive type of forces. So we feel the need of studying Dirac delta function in details. Let us now define the Dirac delta function denoted by delta of x being the argument of delta. We can define the Dirac delta function in multiple ways. Look at it from multiple angles. That is, we can attach multiple interpretations to the Dirac delta function. In other words, Dirac delta function has many representations. In this video, we shall speak of only one representation. We shall define or describe the Dirac delta function from a box function or a rectangle function. We will see how a rectangle or a box can be converted to the Dirac delta function. Let us start from scratch. Have a look at the right slide and see how we can achieve our purpose. Hope everything would be very clear soon. Let us define or think of, that is, construct a function of x, and let us call it f of x, represented by the green straight line named AB at a height 1 by 2 epsilon from the x-axis, epsilon being an arbitrary number. Look at the stretch of the line AB. It extends by an amount epsilon in the positive x side, and so the x coordinate of the point B is epsilon. The line AB stretches also by an amount of epsilon along negative x side, and so the x coordinate of the point A is minus epsilon. Clearly, the straight line AB is centered about x equal to 0, that is symmetrically placed about x equal to 0, because it has equal portions along positive x and negative x. We also note that epsilon denotes the amount of stretching along positive x or along negative x directions. This function, or the green straight line plot AB, is referred to as the box function or a rectangle function. Now, what is the width of the function f of x? That is, what is the width of the straight line AB? It is easy to calculate the width of the function, as you can see in the white box, and it is 2 epsilon. Clearly, half of this width, or alternately half width, is epsilon, and we label the function f of x by attaching the half width as a subscript. And so we have written f of x with epsilon as subscript. A very important characteristic of the function we have considered is its area. I mean, the area that it hides under its stretch, which is a rectangle, as you can see over there. The top line being green, base being blue, and the pillars, that is the height or the sides, are in the red. Let us agree to keep the area of the rectangle, which is the area under the curve AB, to be a constant, and let us choose the constant to be unity. Now it is clear that for this reason the rectangle was chosen to have a height 1 by 2 epsilon and width of 2 epsilon, so that they cancel out while evaluating the area under the curve AB. The area calculation is shown in the red box down under, and it is width 2 epsilon into height 1 by 2 epsilon. So the area is unity. The rectangle encompasses unit area. Let us now mathematically define the rectangle function as given in the green box. It is 0 beyond minus epsilon in the negative x direction and 0 beyond epsilon in the positive x direction, so that its width is 2 epsilon. Clearly, it has a height of 1 by 2 epsilon, which is a constant value in the region from minus epsilon to plus epsilon. And as the width is inverse of the height, the area under the curve is unity. The left slide is the summary of what we have defined and stated just now about the rectangle function f of x with the half-width epsilon as its subscript. Let us focus on the right slide to move ahead. Let me reiterate the main feature of the rectangle function which we would be using over and over again, and it is that the area under the curve is unity, and we would stick to it firmly, whatever be the width of the function. In other words, maintaining area under the curve unity is the bottom line, and we are determined to do that by any means. Our aim is to move to the point x equal to 0, about which the curve or the straight line AB is equally symmetrically spread out. Now, to move to x equal to 0, we have to reduce the width of the rectangle. So let us squeeze it, that is, shrink the half width from epsilon to epsilon by 2. And so now we have to write f of x subscript epsilon by 2 for the new plot. This means the curve, that is the straight line representing f of x, is now stretched by an amount of epsilon by 2 on either side of the x equal to 0 position. So the width of the plot or the curve would be epsilon as calculated in the box outlined in the red. Again, since shrinkage of width would reduce area and we cannot allow it, it is clear and imperative that we increase the height by an appropriate amount to restore the area to unity. This means height has to be set to 1 by epsilon, and the function is represented by the straight line CD stretching from minus epsilon by 2 to epsilon by 2. With this, the area becomes unity as calculated in the blue box. Let me reiterate our mission once again. We are on a mission to reach x equal to 0 point, keeping area unity. The left slide shows the summary of what we did till now in our effort to reach the origin x equal to 0 by reducing the width from epsilon to epsilon by 2 shown in the white box. The height increases automatically since we have promised not to change the area and hold it at unity. Now to the right slide. Since we are sitting at a distance epsilon by 2 from the origin, to complete our mission, we move further towards x equal to 0. Let us move from epsilon by 2 to epsilon by 4 towards the origin. So the half width is now epsilon by 4, and to keep the area unchanged at unity, we have to increase the height to 2 by epsilon. You can see the plot of f of x with half width epsilon by 4 as the subscript. The area is worked out in the box with the red outline, which is obviously unity. One thing is very clear from the discussion. We have to keep area constant at unity, and to do that we have to shrink the width, and so the rectangle or the box becomes narrow, and at the same time the rectangle or the box becomes tall and taller. Let us now complete our mission, That is, let us aim to sit on top of x equal to 0. That is, let us force our way to the origin. In other words, let us make the half-width epsilon tend to 0, as mentioned in the white box. Focus on the plot inside the red box. The function is now infinitely narrow. The width has shrunk to 0, and to keep the area constant, the height shoots up to infinity. In other words, we now have an infinitely high spike represented by the vertical line starting from x equal to 0 and making its way to infinity. And this is the Dirac Delta function. We get the Dirac Delta function from the rectangle function in the limit of 0 half-width. Dirac Delta function is the rectangle function in the limit of 0 half-width. You can see the limiting relation written in the white box, where epsilon is the half-width of the rectangle function. And the relation says that if we make half-width epsilon 0, then f of x is to be denoted by delta of x and is named the Dirac Delta function about x equal to 0, denoted by delta of x. In other words, the rectangle function becomes the Dirac Delta function at 0 half-width. In the left, the plots of various half-widths we discussed have been shown, and the trend is evident. First, the brown rectangle is very wide and stretched out along the x-axis and is of very short height. But if we fix the area of the rectangle and allow it to shrink along x-axis and ultimately fall upon x equal to 0, the origin, then as the width collapses, the height gets gradually increased so that the green rectangle gets more and more spread out vertically while shrinking in the x direction, and the pink rectangle is narrower in width and vertically taller, that is more stretched out vertically. And finally, as you can see from the plot in the right, as the half-width epsilon becomes 0, we see that the function has no spread along x-axis about x equal to 0, but infinitely spread out vertically. So we get a high or tall spike shooting out to infinity. The significant achievement is that we have been successful in our mission of arriving at the origin x equal to 0, starting from a rectangle, and in the end, what we have got is the Dirac Delta function. The only thing we have insisted is to keep the area constant at unity. Unity being our choice. You can see the Dirac Delta function represented in the plot drawn in the left slide. We have to remember that it is the one-dimensional Dirac Delta function about x equal to 0, the origin. Having got the Dirac Delta function, let us now represent it mathematically. Looking at its plot, we find that when x is less than 0 or when x is larger than 0, that is, for x not equal to 0, the Dirac Delta function is 0. But right at x equal to 0, its value is infinity. This is denoted in the box outlined in the green. We recall that we started with the promise of keeping area unity, notwithstanding the shape of the function, that is not depending upon what half width we care to choose. This obviously means that in the end too, the area should be unity. So the manner in which we arrived at the plot of the Dirac Delta function ensures that the area under the Dirac Delta curve is unity. This is mentioned in the box with a black outline, where we integrate over the x-axis from minus infinity to plus infinity, that is, collect all the values of delta x and add them, which gives us the value of unity. Clear that the contribution to area, that is the value of unity, comes from the point x equal to 0, which is the point where it is non-zero, in fact infinity. This is indicated in the blue box, where we integrate from minus epsilon to plus epsilon through x equal to 0, where epsilon is a small positive number. Again, if we exclude the x equal to 0 point and integrate over all other points on x-axis, then obviously we get a 0, because then we are excluding the very point that contributes. This is mentioned in the red box. Dirac delta has a peculiar property. It is not properly defined at x equal to 0 because we say that its value is infinity, and infinity is as large as we please. It depends on the large value that we choose at our pleasure. In other words, it is undefined at x equal to 0. Again, at x not equal to 0, we do not find it because here it vanishes. Its value is 0. So the question is, how should we deal with such a function? Particularly, we are afraid of the fact that its value is infinity at a point and we cannot handle infinity. In physics, we always look for avenues that give us finite values, because though we are quite efficient in dealing with finite numbers, we do not know what to do when we plunge at infinity, a singularity. And thus physics always avoids, in fact carefully avoids, infinity. In this Dirac delta function case, we have a way. We can avoid infinity because of the clever choice we have made in the very beginning of the lecture. And what is it? Whatever you do with the function, be sure to keep the area constant, and for convenience we chose it to unity. This is what we did. So if we integrate over the Dirac delta function, we get the total area, and it is a finite number, the constant we started with, that is unity. It is a great thing that we have avoided the infinity that was threatening us. We can also use Dirac delta function in spite of it carrying an infinity. We can exploit its finiteness, and due to this property, the Dirac delta function has earned a significant place in physics. We have been discussing the Dirac delta function erected about x equal to 0, which is an infinite spike at x equal to 0, the origin. And this we got because the rectangle function we started with was drawn about x equal to 0, and the rectangle was squeezed along the x-axis to point x equal to 0, the origin. Based upon this prescription, or following the same guideline, let us build the Dirac Delta function about x equal to a. Let us suppose that instead of x equal to 0, x equal to a be the point of our present concern. We are now interested with the point x equal to a. So the rectangle function is now drawn about x equal to a. Previously it was drawn around x equal to 0. And then, following similar procedure and arguments, we come at the Dirac Delta function about x equal to a, which will be an infinite spike erected or constructed at x equal to a, and this is shown. Note that for x not equal to a, the value of Dirac Delta function is 0, and at x equal to a, it is infinity. Also, the 0 width and infinite height are coordinated in such a way that it gives the area under the curve to be unity, as in the previous case. Clearly, the Dirac Delta function about x equal to a is just a translation of amount a from the x equal to 0 point along the positive x-axis. This mathematical representation of the Dirac delta of x minus a is mentioned in the box with a green outline, and it can be obtained from the mathematical representation of Dirac delta of x, simply replacing x by x minus a. The finite value of area that the delta function is associated with stems from its contribution at x equal to a. So, while integrating along the x-axis, we have to be careful as not to exclude the point x equal to a, because it is this point that only contributes to the area integral. This is mentioned in the box with brown outline. If we omit x equal to a point, the integral would give a 0. This is described in the box with red outline. The one-dimensional Dirac delta function has been defined and discussed, and this has been quoted. Let us extend the idea to 3 dimensions, and then what we arrive at is the 3-dimensional Dirac delta function. Let us represent it mathematically. In the one-dimensional Dirac delta function about x, let us replace x by vector r. So what we get is the 3-dimensional Dirac delta function, delta of vector r, whose value is 0 for vector r not equal to 0 and infinity for vector r equal to 0, in such a way that the area under the curve, that is integration over delta of vector r d of vector r, is unity. Integration being over all space, since we are considering the 3-dimensional space. Note that d of vector r is actually d of tau, representing volume element as specified in the last line of the slide. We had earlier defined and discussed what we mean by Dirac delta function of x minus a. It is an infinite spike at x equal to a, and the mathematical representation for it has been quoted. Let us extend the idea to 3 dimensions. In other words, we write down the Dirac delta function of vector r about vector r0. Dirac delta function of vector r minus vector r0 is 0 for vector r not equal to vector r0, and it goes to infinity for vector r equal to vector r0. And this occurs in such a way that the area under the curve is unity, integration being carried over all space. Here too, d of vector r is actually d of tau, that is the three-dimensional volume element. Let us now find the dimension of Dirac delta function as wanted in the question you see in the left slide. The features or the characteristics of the Dirac delta function, delta of x, has been written at the beginning of the right slide. To solve this problem, that is, in order to find the dimension, let us focus attention on the area integral in the box with blue outline, the right-hand side of which is unity, and the number 1 has no dimension. So essentially we have product of Dirac delta of x and d of x on the left side and 1 on the right-hand side. So the very next step gives the result. Dimension of Dirac delta of x is 1 by x, that is 1 by length, that is inverse of length. Now since x is the argument of delta, we can obtain the general formula which has been written in the green box. So dimension of Dirac delta function is the inverse of its argument. Let us use the formula to find the dimension of these Dirac deltas you find on the left slide. Dirac delta of x minus a is the inverse of x minus a, and since x and a have same dimension, we can equivalently write it as simply inverse of x, that is inverse of length. Dirac delta of p minus p0 is inverse of p minus p0, and since p and p0 have same dimension, we can write it simply as the inverse of p, that is inverse of momentum. Dirac delta of k minus k0 is the inverse of k minus k0, and since k and k0 have same dimension, we can write it as simply the inverse of k. Again, we have quoted the famous relation P equal to h cross k, from which we have k to be P by h cross. And again, h cross is angular momentum r cross p. And so, simplification leads to 1 by length as the dimension or unit of k, and therefore the dimension of delta of k minus k0 is simply that of length. We now proceed to find the dimension of the delta functions you see on the left slide, and they are all three-dimensional delta functions. So we have to split them into 3 factors and proceed to find the dimension of 3D delta functions. Now to the right slide. The formula has been shown. The dimension of Dirac delta function is inverse of its argument. Now delta of vector r is the product of 3 deltas, namely delta of x into delta of y into delta of z. And so the dimension turns out to be 1 by length cube, that is inverse of volume. Similarly, the dimension of Dirac delta R minus R0 can be obtained as shown. We now switch over to finding the dimension of Dirac delta vector P minus vector P0. Spreading it, we express it as the product of three Dirac deltas, namely delta of Px minus P0x into delta of Py minus P0y into delta of Pz minus P0z. And this is nothing but 1 by P cubed, that is inverse of momentum cube. Coming to the dimension of Dirac delta of vector k minus vector k0, we again can split it into component factors, and the dimension is thus 1 by k cube. Since dimension or unit of k is length inverse, the answer turns out to be length cube, that is volume, as the dimension of Dirac delta of vector k minus vector k0. Let us graphically and mathematically represent the Dirac delta function about x equal to minus a. Now over to the right slide. We have recalled the graphical and the mathematical expression of Dirac delta function about x equal to a, that is Dirac delta of x minus a. Clearly, the result will be obtained by substituting a by minus a, through which we would get Dirac delta of x plus a. The plot has been shown in the blue box. We have located the point x equal to minus a, and it is at this point where the Dirac delta x plus a would be infinity. So we have an infinite spike there, that is at x equal to minus a. Now, the mathematical representation is shown in the green box. At x not equal to minus a, the Dirac delta of x plus a is 0, while at x equal to minus a, its value is infinity, in such a way that the area underneath is unity.